Right, recording has started.
Okay, test. Can.
I can.
Okay, okay, I was on grid traversal. It's basically just BFSing the grid. So you take each thing like a vertex and you take this as the graph. Yeah. Okay, and Dijkstra. Okay. Basically this one is algorithm to find the shortest path from node X to another node in a weighted graph. So like for example this one. So let's say oh okay, it's gonna explain. Okay, let's say we want to find the shortest path from node 1 to node 7. Can one of you like try and think of how you're gonna do so? Okay, let's get Zixi. Zixi.
Good morning.
Yeah, how will you do this? How will you find the shortest path from node 1 to node 7?
I'll use Dix.
Uh okay. Let's assume that you don't know what Dijkstra is yet. Zixi.
What? Okay. I would brute force every solution.
Okay, yeah, that's a viable strategy if you have the time. Like if you just go for like you try every single path that leads to from 1 to 7, but that's kind of slow. So okay, I know like some of you here already know what Dijkstra is, but for those that don't, I'll just like go through Dijkstra. Um Basically what Dijkstra does is you explore nodes in BFS manner and you keep track of the shortest distance from source node to other nodes. Use a distance array. Yeah, and update the distance if you find the shortest way. So this is like a greedy algorithm. Basically, okay, we'll use this like visualization here. Like when we are at one node, we queue the neighbors are in BFS and you update their distances. So you have a distance array and you have like the queue that's used in BFS. So let's say we find a new shortest distance, right? The one that's already there is longer than what we have already found. We just update it, and you add the queue to be processed, like how BFS is done. Now, after we're done with the current node, right? We how do we choose like the next one in the queue? In this case, here's where the greedy comes in, right? We choose by the shortest distance, so we're guaranteed to find the shortest path. Uh, convince yourself this is the case. Okay, so we go back here. I'll go through the intuition here again. So we go by BFS, right? So these two are in the queue to be BFS next. How do you choose the one that's in the queue? Basically, in normal BFS, it's just like whichever one gets put in first, you explore next. But for Dijkstra, you explore them in the order of their weights. So the shortest distance get explored first, and this therefore results to find the shortest path for every like node. Okay, and anyone want to contest the intuition? Okay, so yeah, so this is the intuition for Dijkstra, and we'll just move on. Okay, so there's a visualization here. So we explore the shortest path first. We explore shortest path first. Uh yeah, and we choose the shortest one. So then BFS, right, we go here and we update the distance array, so 2 and 4 respectively. Then we go to the shortest one, so it's 1 because notice 1 is less than 15. So we choose the shortest one, and now we finish the graph. Yeah, and the implementation for this is quite simple. Instead of a queue, you just use a priority queue. So here's an animation of how the extra works. Y'all can look through this. So we can see algorithm at work here where we are taking the shortest path first in the priority queue and updating distances when it's less than the current one. Yeah, so here we choose the shortest one because 7 is the and so on. Okay, any questions for Dijkstra? Anyone has any questions? No? Okay, there's a problem called Dijkstra on Codebreaker. Go AC it. Can I just like quickly check who has AC Dijkstra and who hasn't? Hello? Have all of you AC Dijkstra, like the problem on Codebreaker?
I have AC Dijkstra.
Zixi? Qin Zixi. Have you AC Dijkstra? Okay. Josiah, do you AC Dijkstra?
Yeah, technically. I'm probably going to do it again.
Yuvraj, what about you? Sorry? What?
Wait, I don't think I have it.
You haven't? Okay, it's fine. We'll wait for you. We'll give you like 10 minutes to do it. Sure.
It's underwear.
Wait, no.
Give 10 minutes to
Actually,
AC Dijkstra.
that's a bit too long.
But that's
Since the rest of you have done already, okay, wait. Yuvraj, maybe after today you go and do the problem. But you understand how this algorithm works? Do you have any questions for me?
Yeah, just one question. So right, for the Dijkstra, how do you actually like implement it?
How do I actually
Yes.
what?
Implement the code in a problem. In a problem. How do you implement it?
Okay, because by nature of Dijkstra, right? It's you find the shortest path from like one node to any other node. So you basically have to just like use it where the problem needs you to use it. You can't just like put it in every single problem and like I don't know. Implementation wise, you're supposed to like do it yourself. Oh wait, are you asking wait. Okay, so for Dijkstra, right, what ends up happening is that you have a distance array, like and it computes the distances, the shortest distance from one node to all nodes in that distance array. So where you will use it is, I guess, like just directly accessing the distance array. I don't know. There's many like there could be many like possible places where you would need to use it, or like different ways to use it. But that's for you to like figure out when the problem needs you to do it. Okay, I'll just move on from here. This is the implementation. We can see like, okay, I'll just attempt to explain this because I didn't write this. It was from like last year. Okay, so we see here's the adjacency list, and we are doing BFS over here. So while the priority queue is empty, we push the neighbors, and we pop the first one. Then we explore the first one, and you update the distance array. Okay, any questions for this? Okay, yeah, here this the all the priority queue stuff. Here we set the distance array to all like -1, and we explore the first one and make it 0. Basically, the first one is like whichever node that you want to like start with lah. So here this is like normal BFS code will also look like this, but it's just this part would be like anything else. Dijkstra is just BFS with like this thing. And what this does is that it checks if like the current one is -1 or or we see here the comparison like plus h which is less than the current one, then we update that current distance and then we push the neighbors. Okay, yeah. So over here we process the top node of the PQ and we store distance and node in the PQ. So it sorts by distance. And then yeah, we pop it, then we process it and so on. Okay, and here this is specifically for the Dijkstra problem, where the answer is distance of V. Yeah, from node 1 to node V, but it could be anything else depending on the problem. Okay, Floyd-Warshall. Since no one has any questions about Dijkstra, I'll just move on to this. This it solves like all pairs shortest path problem. Shortest path from any node to any other node. So we notice like Dijkstra is just one node to every node. This one is any node to any node. Yeah, the time complexity is n cubed. No, not really. We don't really care about space complexity, but if you're interested, it's n squared, and you'll see why later lah. Okay, this one actually uses like, okay, basically, for each node, right? We set like an intermediate node. We select two pairs and we select intermediate node, and we just see like we just see if the distance from I to the intermediate node plus the distance from the intermediate node to J is like less than the current one. So like relax. Yeah, here we see that from I to J is 10, right? But from I to K is 2 and we set it to 2. Then K to J is 5 and you change it. Yeah. You basically change this IJ to 5. So for it, yeah, so the order, right? Basically the outer loop must be the intermediate node because you are like you have to process this one first before doing this. Okay, so I don't really know what this is talking about. Basically here, right, because we're changing the value of K, we're changing like all possible like distance A and B as the shortest route. So if once we're using A and B as the intermediate, it would be the shortest route. Yeah, and if we have, so we want it to be like changed whenever we find a new shortest route, and therefore we can't use it as the outermost loop, because it will never be changed once the loop is done. So we want to loop all K, and then loop all I, loop all J, so that if a new shortest route is discovered with a new intermediate node, you can update I and J. Does that make sense? I think I explained it quite shit, right? Y'all any questions? No? Okay. Yeah, so we can see the okay, wait, sorry about that. Here we can see the like the implementation. We can see the K is the outermost node and then outermost loop and then I and J. And we basically just like set every single I and J to the minimum distance of I to K plus K to J and this of I and J. So this part here is what the algorithm is doing. It tries and sees if the distance from I to intermediate node to K to intermediate from I to intermediate node and from intermediate node to J is shorter than the current distance IJ, and it just updates that. So go by intuition, for every single intermediate node, we check I and J and we try and make the shortest path. And like earlier, I didn't really explain it. We can't put I on top because once you finish iterating all K and I still has stuff left behind, like you can't change like I to j anymore, even though there's a new k that can have a smaller distance than the current one from I to j. Does that make sense?
There are multiple intermediate nodes.
Sorry?
Oh, there are multiple intermediate nodes.
We are checking for all intermediates. So like from the first intermediate 0, we try I and j to intermediate 0. We try I and j to intermediate 1, then to all the way to n. So we are brute forcing every single way.
Oh,
Yeah. Okay, we try this lah. I'll give you all like 10 minutes ish to do this problem set now. Ideally, you should be able to AC Ash list, Ash matrix, Dijkstra, split honey, Dino. Yeah, it's not. It shouldn't be that difficult. I'll just like wait here for 10 minutes. Just like continue is fine. Wait, I can't find the slide. Oh my days. Oh, okay. Wait, my bad. I forgot to like share the problems. Okay. I'll give y'all like 5 more minutes to attempt these problems. Okay, if y'all have any questions regarding these problems, like do ask them also. Or any questions in general for graphs, yeah, please ask them. Otherwise you'll get like quite lost in the next one then. Oh, okay. Yeah, also like please do like try these problems. Unless you all have done them already, which I don't think so. No, I'll just like reiterate, right? If you have any questions, like please do ask them now before we get into the next topic, which is new and like quite difficult lah. And you will
Is there a
get
place
quite
that we
lost.
can? Sorry.
Sorry?
Is there a place like we can submit our code if like it doesn't work? Or like
Code breaker, what? Like
like if you want like
oh,
y'all to look at
okay.
our code, where do we send
Just send it here, cause advanced is a smaller class. Beginner has
Okay.
like a forum, but I it's fine. Oh wait, there's a forum here also. So okay, I just posted in questions. Like you see under advanced stuff, there's a channel called questions, right? Yeah, I just posted there. Like problem, like as the title, and then your code. And then we'll take a look at it.
Wait, so do I post in the forum or like in the advanced chat?
Forum. Under advanced, there's a questions forum. Okay, wait. Oh. Jordan, have you posted your question? Jonah.
Oh, I don't like actually have like any problem. Just like in the future if there's any.
Oh,
Yeah.
okay. Well then, if there's nothing else, wait. Teacher, can you like carry on with trees first? I need to like settle some beginner people, like their accounts not enabled.
Alright. Okay, yeah, so wait, can you share screen?
A bit harder. Can you just share? Trees one. It's in
Okay,
the
yeah. Hold on, let me find the thing first.
Okay, yeah, you can just start now, I guess.
Wait, no, Lashawn, I can't
Since no one has any questions.
I can't like share and record at the same time because it's just
Oh.
like we
Okay,
paused
wait, let give me a moment. I'll share for you. Okay, everyone can see. Alright, everyone can see my slides. Yes? No? Hello?
You can see.
Okay. Okay, there's trees here. Vision.
Alright, so
Yeah, you can
Alright,
start.
so we're gonna start on trees. So basically trees are basically more advanced graphs in a way. So like before we begin, like at least make sure you know like your basic stuff like your adjacency lists and DFS and all that. So basically trees are a special type of graphs that are and is often used in you can often find them in like more advanced problems. So basically trees are, as you can see, maximally acyclic and minimally connected. This means that so let's say if we have a tree of n vertices, there will only be n minus 1 edges. Right, next slide. Yeah. So first of all, how do we make trees? So let's say if we have a normal graph and we want to turn it into a tree, we can use a minimum spanning tree or a maximum spanning tree, but it's basically the same thing. So let's say if we have this graph and we want to turn it into a minimum spanning tree, it will be like this. So we basically try to make sure the maximum number, in this case like 7, is as low as possible. Alright, so how do we do this? We use Kruskal's algorithm. Basically we take all the edges and we sort them. So because we want to find the minimum spanning tree, so we sort them with the lowest first. So now we just go through all the edges, and if it connects if it connects two unconnected components, then we use it. If it's already connected, then we just skip that edge, because you don't have like additional connections in trees.
Okay, so like if you imagine this, right, it's like you have an edge, like all the edges are in an array, and it's sorted from lowest cost. And to begin, all the nodes are unconnected, and you take the first one, which would definitely have the smallest cost, and it connects to things, right, and so on. You just keep on taking. But if the next one in this array connects like two already connected ones, it is definitely the case that it is a higher edge weight than the original one connecting the two, because the original array is sorted. The problem with this is that, how do I check whether like it's two previously unconnected components? Here's where like we need to talk about UFDS. It's a technique, I guess.
Right, so UFDS, if you might have heard about it in like the editorial just now, but basically it allows us to basically merge different vertices together and keep track of them. So like, let's say we have a bunch of vertices and they are all separate. So we can basically connect them together.
And what UFDS lets you do is that if you have a connection like this, you can find like the head-ish of the entire set. So if I query find set of 3, find set of 2, find set of 1, they all link to 8 because it's directed this way. But over here, like here, if I query 2, it will return 3. So in this case, these are two disjoint sets. But when you merge them, now they are one set.
So basically, if the set of something is the same, it means that the two things are in the same group.
Yeah, but we realize here that we don't seem to need to know like this entire path. We just need to know that 2 links to 8. Like, I don't care that it goes like that. I just want 2 goes to 8. So the path compression, just like, yeah. So in this case, I don't really care about the order in which it is going to 8. I just want to know that 2 goes to 8, 1 goes to 8, 3 goes to 8, and this is one set. Okay, here's like one case, right, where 4 isn't linking to anything. When you find set of 4, like it just links to itself. So that's how we initialize the UFDS. Merge 7 into 4, merge 4 into 2, and here we have path compress. So yeah. And we see that because 2 was already compressed, it only took 3 steps. So here's the implementation. We keep an array of like parents, which is basically like 8 is the parent of 3, 8 is the parent of 2, 8 is the parent of 1. And in the beginning, we set the parent every node to itself, and we can see, right? So here, 5 isn't connected to anything, so it's its own parent. 6 is its own parent. 9 is its own parent, and so on. So we initialize it like that. Here, find set is a function, right? So we recurse to the parent and like path compress. So we first need to check, right? If the element is its own parent, then you just return x, and you recurse to its parent and you find set of that, and then you path compress this. So if I go line by line, here is the base case. If parent of x is equal to x, you just return it because it's like the same. And then else you will return parent of x and then recurse to find set of the parent of x, and you set parent of x to the recurse function, and which eventually it will lead you to this lah. So if I use it on this over here, if I first find a set of 7, it will recurse to 4, and then to 2, and then to 8, and then path compress 7 to 8. We can see how this works, right? Okay, next is merge set. Let's say we want to like set A's parent to be a leader of set B. So like in this case it's like in this case we're gonna use merge set as like merge 4 to 2. Yeah. So we look at this function. We use the find set function to like find the parent of like X, and then you take the path of that and you set it to Y. So we can see how this works like over here. If we take the parent of 7, which is 4, and you set it equal to the parent of 2, which is 8. So and then yeah, that's how these two functions work. So like we said, to check whether they're in the same set, you just check whether they have same leader or parent. So if find set X is equal to find set Y, then they are in the same like set. Okay.
Alright, so back to our minimum spanning tree. So basically, remember when
Wait. Any questions on UFDS?
It's only for
Right.
non-weighted, right? You just take the weighted tree.
Huh?
whether
This
the edges
section.
are weighted doesn't really matter,
It doesn't matter. Here you're just purely finding.
Oh, because you just find the parents.
because you're,
Yeah,
you're
you
just
just find
finding like
parents.
the connections. Right, any other questions? Alright, I assume that's a no. Alright, I think we can continue.
Okay, so yeah, we'll just continue.
Alright, back to our minimum spanning trees. So basically now when we try to connect the unconnected components, we have a fast way of checking if things are connected. So basically when we have an edge, we check if the two nodes that the edge is connecting is already connected. If it's already connected, we just skip that edge. If it's not connected, we just connect it and use our UFDS to connect it.
Okay, so try problems, car and SimCity. Actually for now just do car lah. I'll just wait until everyone ACs car. Okay, any like questions on the implementation of minimum spanning tree?
Like, how do you like actually implement like minimum spanning tree?
Basically,
Uh,
like to store the edges, you can have like the common ways to have like a pair of an int and a pair of int and int. So basically, like the first int is going to store the distance, so you can sort it, because it's when you sort something, it sorts by the first number first, and then the two other integers are the IDs of the two nodes that it connects. So like, and then you basically sort it with the STL sort function.
Yeah, cause like remember we're just like putting stuff into an array and sorting it. So you just like input it like as if every edge is like it's like its own like thing. So for example, if
I
like
think
your input is sorry.
Wait, no, you go first.
So like for example, if your input is like 1 to 2, like there's an edge connecting 1 and 2, and it's of weight 3, then you just store the weight as the first one in the array. So it's like pair int. So you have weight and then the two like places that it connects to, and then you sort that array so that it sorts by the edge weight.
Sorts by weight.
Yeah.
Oh, okay.
And then you implement UFDS to go and to check whether the two nodes are connected already. And the way you do that is you just query the parent, and if they're unconnected, to connect them you just like merge set. That makes sense?
Oh, okay.
Yeah, I don't understand. If they're unconnected, how come we can just merge them?
UFDS allows you to do that. So like if they are unconnected,
Oh,
you
then
have like you use the merge set function. Okay, I'll go back to merge set. So here merge set, basically what this does, it sets the parent of like X to be equal to the parent of Y. So
but how you know it is meant to be connected?
because you are trying to find the minimum spanning tree, and basically you're assuming that okay, I'll go back to the tree.
You're assuming that all paths exist. Oh,
Where's the tree? Okay. So like we are basically assuming that none of the paths exist from the beginning, and we have all these numbers in an array, and we just start from the smallest one, so like 1, and it connects these two, right? So yeah, we just like connect them, and then we set this parent to that, like we merge set, we do merge set, then so now it's like a bunch of disconnected like things, right? And with this node connected to that one, and then we go to the next smallest, which is 3, and then
No,
it
it's
connects
2.
these
It's
two,
2.
and then 3 is
It's 2.
Is
It's
it
2.
two?
it's 2. My bad. So now 2, right? These two are unconnected, so you just set you merge set this one to this set, and then you have the same parent, and then 3 and so on. So you're basically, but in this case, right, 3 is already connected because this whole thing will return the same parent. So yeah, you wouldn't need it.
Wait, but the weights are different though.
Yeah,
Like,
so
the
that's
weight-
why you take the minimum. That's why whatever it is, you take the minimum,
Oh, okay.
because you're trying to find the minimum spanning tree. So when you take in edges, it's like in order of how small it is. So that's why we're processing 1, 2, then 3. But in this case, this 3 doesn't need to be there because it will return the same parent to this set, because this set is already connected. Make sense?
Yeah.
Okay. Yeah, go do car. Where's car? Yeah, car. Anyone has any other questions on UFDS and minimum spanning tree? Yeah, I'll give you all 20 minutes actually. It's like MST takes like a bit of time to debug if you get it wrong. So yeah, don't be afraid to like ask questions or like post your code in questions for it to be debugged. Or if you don't understand anything, like please do like ask.
Wait, for UFDS,
Yes.
you just like merge find set and merge set.
Huh?
Like you just like merge the two functions together. Like you don't exactly need to.
No, you can't, because you need to use find set for merge set,
Oh,
because you have to find the parent first. So like you are setting the current node's parent to the parent of the other node.
And you have to check like whether they're in the same group.
oh, okay.
Wait, I don't get it. I don't get car. Why is it that it has to be minimum mileage but not shortest distance? What does that mean? Hello?
It means that basically, because like you have a bunch of like road lengths, and then like your car can only like, and then your car can travel a certain like road length. So basically, and because of that, you want to basically make sure like the longest road length is as short as possible.
Oh, okay. So it's basically just okay.
Yeah.
Why don't I get this unusual DM activity alert?
Wait, hold on. LaShawn, you look at the logs. There's some guy like the 3A54WS6 guy, like that looks like damn sus.
What?
You go to like the logs and then like the turtle logs.
Oh,
Is it that? Like
Oh,
I haven't seen that guy
Like
like
what? Who?
3A54WS6ED5RF6TUVY. I don't.
Ban him lah. Just ban.
who's that?
Nobody knows.
Don't know, suspicious person.
They got flagged by Discord, so
and it's like a very new account.
But we also can't like do anything because it could just be like someone doesn't have Discord and just create the
no, it's just ban first.
Wait, is he like in any calls?
No.
Can you just DM him?
Josiah, you DM. Ask him to identify himself.
Bro. Oh, where is his? How do I do this?
DM him, yeah.
Try to find a general chat. Ah, I found it. It's not even online.
Bruh. Can you just
There's
DM
no
him?
this guy called. There's a guy called YN. ask you to change his name number.
Huh?
How do you? Why can't I DM him? Oh, I can. Okay.
Oof.
Nice.
Okay, I'm gonna stalk your submission now. Who is this? Why no one doing car?
Bro, the shot went not that fast.
Oh,
We're like really slow.
it's not that hard. It's just like
For you.
Yeah, it's hard to understand. It's like, how do you do that? What?
okay, wait. You need me to go through anything again?
I think I just need like time to understand. Yeah.
Can. No, like wait, what do you not understand about it?
Like it's like how like you link different parts of the code together. Like each individual part like makes sense. Like I know I need to like sort by weight.
Oh.
Then
Basically,
I just
how
need
you
to, like-
check whether two edges are connected already, you just check whether they have the same parent. So you use the find set, and if find set x equals to find set y, then they have the same parent.
Oh,
Yeah,
let me just try implementing it first.
yeah, just try implementing. I guess like, okay. How much time do y'all think you need?
Maybe 10 more minutes. I don't know.
10 more minutes. Okay, I can. I don't think we have a lot more to go through. Oh, wait.
No, there's like
Oh.
day 4 is also trees, so we can like leave some of the stuff for later.
Yeah. Oh, actually, I speed ran most of this. Okay.
Like stuff like 3DP and like ancestors, we just leave to Thursday. Leave to like
can.
day 4.
We pretty much did like everything today.
Yeah, I basically just like speed ran all of this already. Oh my.
I think that
Joshua, I don't think we're that fast.
Yeah.
Now what we're
I
gonna do in the
realized.
afternoon?
there's like still math, right? It's like math is in the day 1 folder.
Hey, if you need me to re-explain any concepts, I can go slower. Yeah, I'm sorry. I went like quite fast.
Can you just go slow in general? Too?
Can. But like, if you need me to re-explain anything, like from graphs even, because I assume most of you know what graphs 1 is already.
What does Graph 1 even talk about?
Graph 1 is BFS, DFS, Dijkstra, and Kruskal. No, Dijkstra and Floyd Washoe. What?
I completely forgot how to sort. I'm looking at the reference now.
Oh, are you using vector array?
Array.
Array is just like
Okay.
you sort like the array name without the without without the square brackets, and then like array plus like the size of the array.
It's like sort a plus n if n is the size of the array. Node is 0 index, so this is a plus 0 and like a plus n is like n minus 1. Like
Isn't it just like array dot begin, array dot end?
no, that's for vectors.
That's vectors, right?
Oh, never mind. I'm using a vector.
So right, just like a root, like they also like other
Here's
vocabs.
slideshow.
What?
Here's slideshow the
Okay.
yes.
So just like a root, there are other vocabs such as like a parent. Yes, a parent. So for a node 4, like here, 2 is the parent of 4. And the opposite of parent, they're also children. For the children of 4, there are like 8 and 9. So a root is basically a node that has no parents. The one node that has no parent. And for leaves, there are like no children. There could be a lot of leaves, but there's only one root. So rooting a tree. Actually, a tree can be arbitrarily rooted at any node. You can select a node at like 10 or 13 or 4, whatever you want. It depends on the question. But usually we just set it as like 1. So you see, right? It looks like 1 is the highest, but I can set it at 2. Let's just try 2. Not just become like this. It's tilted now. Now 2 is the root. And 1 is now the children of 2. So like, you may be wondering, what's the point of rooting a tree? It just weird. It allows us to give other nodes like properties of depth and like subtree size. And then you can do DP on a tree. You have to recurse from a parent node to a child node. So you will know the parent-child relationships in the tree is important. So you DP from the children to the parent, or you can do DP from the parent to the children. It depends on the question as well. Rooting a tree. You have to use DFS to root a tree. We usually root the tree at 1, so we can call DFS 1, -1. The -1 stands for the parent. Yes. So we don't want to visit the parent. So if I equals to P, we just continue. We just skip it. Wait. Is that all?
Wait. Where is rerouting a tree?
Rerouting is like om nom nom 2, right?
Is it just pre-order already? Is it just that little?
I mean, do you want to teach pre-order like then we have more time in the afternoon that I can like let them do more problems? Okay, just do pre-order and post-order now lah. It's fine.
Any of you have any questions on rooting a tree and rerouting?
Oh, no, we haven't taught rerouting.
There's no rerouting.
Rerouting is later if I'm not wrong.
Yeah, it's in om
Yeah.
nom nom 2 is much later.
So we're
Yeah,
teaching
Yeah, anyone
pre-order.
have any questions on rooting a tree, like the code to root a tree?
I assume it's a no.
Okay, well.
I guess we can move on. So we are moving on to a pre-order and post-order traversal now. pre-order. The order basically a tree visited in the DFS. Like, yes. For pre-order, you visit is children first. No. If visits is root, they record down the root, then they go to his children. Like this. Yes. You just do a DFS. Then you record down every visited node. It's a very simple code. It's just DFS. It looks very similar to DFS. You just change a bit. So for post order, we pretty much do the opposite of a pre-order. We record down the children first instead of the root. So you start from the root, you go down to his children, the left children, and it's like get at the bottom left node here. See? You go down here, you record it, now you go back and record this node, the children. Now you go back. So the only difference is that pre-order records down the order first, of the root first, and post-order records down the order of the children first. Yeah, that's the only difference they have. It's also DFS. What can pre-order and post-order do? It's just sub-tree to range you can do with pre-order. Actually, you can do with post-order as well, but nobody does that. And post-order, you can do topo sort. Do you guys know what's a topo sort? Topological sort.
No, what is a topo sort?
So a topo sort, it's basically you visit every single children first. Wait, yeah, you visit every single ancestor first before you can visit the children. Especially in a graph, like. So you see in a graph, there could be like two ancestors of a single node. A node could have multiple ancestors, because it's not a tree. So you have to visit all the ancestors first before you can visit the children. You can record down the order of the children. So I think we'll discover that discuss that later.
Okay, so basically like pre-order, post-order are just like methods to help with doing other stuff. And we're just like teaching the methods now, and we'll get into depth with where they are applied later when we get into 3DP and all that.
Like
But same with subtree to range. Subtree to range is also another method, so there's nothing like how to say, like it's not like Dijkstra where like it's a very obvious use case. It's just this like just one way to do something.
Like the
To
tool is
help you
just
do something.
traversal on the tree. It doesn't do anything. Like you have to do something for it to be useful.
Yeah, it's like DFS. DFS doesn't do anything on its own. When you like greedy when you greedy DFS, it becomes Dijkstra. So this is like the same thing. You have to like do
I
stuff.
think your voice is like echoing. You're -2.
Everyone's is. I think it's because William is like sharing his audio.
Yeah, so wait, we don't want to get into 3DP now yet, right?
Yeah, not now.
So I don't know. We don't have anything else. We're like done for AM, I guess.
Wait, do we give them some more time to like do car and SimCity? Wait, Brian, can you say something so I can test the audio? Hello?
Hi.
Alright, okay, the audio works. Alright, let's get started. Alright, so math. Alright, so like first we have a recap on all the data types. So yeah, basically that's it. So you have your char ints, your char short int longs, and then like in 128 we usually don't use in 128 because you can't see in and see out to it normally, so it's very complicated to use. Unsigned numbers are basically like they don't go negative, but they can go like double the positive. And then for floats, we don't use them much. And then yeah, we have all your operators. Alright, so like here's some stuff about mod. Basically like, because like if when we are working with a lot of big numbers, we usually the question might ask you to use mod so that it doesn't overflow. So if you're going to like add stuff or multiply stuff, you have in order to like prevent integer overflow, you have to basically mod at every step before you do anything. Alright, so first, the first thing for math will be exponentiation. So let's say you want to calculate 4 to the power of 5. Yeah, that's easy. And then let's say now the question asks you 3 to the power of 128. It's not easy for us, but it's still easy for computers. But if the question asks something like this, then you're going to TLE. Because let's say we want to calculate x to the power of n, it's going to be on time, which is too fast. So we're going to look at the question on Codebreaker first.
Tinchen, are you recording or
Yes, I'm
just
recording.
checking? Okay.
I'm recording. Alright, so let's say we have this question. We have t test cases, and every time we have to calculate a to the power of b. So in this case, our time complexity is going to be like tb, because we're going to have to multiply a by b times every time we want to solve one test case, and then there's going to be t test cases, so it's going to TLE by a lot. So how do we fix this? Well, if we can make an observation that, let's say that if we want to calculate, if we just want to calculate x to the power of n, we can do this. We can do x to the x squared and then to the power of n over 2, which is, and like if you take a year 3 math, you know that it gives the same thing, but now we've like effectively half our power. We have half our power now. So this is basically what we're trying to do. We're trying to we're basically trying to like cut down half every time. So like let's say we want to calculate this. Alright, let's hold on. Oh. Wait, hold on, let me say want to calculate 4 to the let's say I want to calculate 4 to the power of 5. It's normally we have to multiply 5. We have to multiply 5 times, which is quite slow, but we can basically use this. We can actually make use of this by reducing the number of times. So let's say 1 to 4 to the power of 4, we can just do this. We can merge it together. And because it's all the same thing, if we can do this in just one step. So we basically like half our complexity. We have, so now it's 16 to the power of 2, and then we can just go to 256. So this basically reduces the complexity from O(n) to O log n, which is much faster, and it allows us to pass this question. So how do we code it? So basically, we just we just follow this table. So if it's even, if n is even, we just square x, and then we calculate x to the x squared to the power of n over 2, and we basically just repeat this until n becomes 1, and then we can just return x. And then if n is odd, we can just minus 1, which will give us an even number, and we can continue. So yeah, this is the code. And then you can go try exponentiate.
I can share my.
You want to share yours?
Okay.
Okay, you just.
Wait, do I need to record?
No, I can record for you.
Okay. So, anyways, bits and pieces. So basically, computers will store integers in binary base 2, but then right here we like to do calculations in base 10.
Wait, Brian,
So for example,
can you like full screen it? Like slideshow?
okay. So for example, like 24 is 2 times 10 to the power of 1 plus 4 times 10 to the power of 0. This is how we express it in the decimal system. But then we need like computers want to do it in binary. So they'll express 24 as like 1 times 2 to the 4 plus 1 times 2 to the 3 plus 0 times 2 squared, 0 times 2 to the 1, and 0 times 2 to the 0, which adds up to 24. So they'll express it like this: 11000. The rightmost digit is the power of 2 to the like number in front of 2 to the 0, and then this one is like the 2 to the 1 place. This one is a 2 to the 2 place, and this is a 2 to the 3rd place, and this is 2 to the 4th place. So because numbers are stored in binary, they are like operations that manipulate the binary bits. So for example, bitwise AND means that each digit gets like, means that if there are 2 numbers, then the final number will contain the end of like each digit. Wait, how do I explain it? Basically like it means that you take each digit and then you process it. And then right shift just means that you move the digits to the right, and left shift means that you move the digits to the left. Then not means you invert each digit. So as an example, right, if we have 11000 and we take the not operator, it will end with 00111. So signed integers are stored in 2's complement, which you can read this chunk of text. Basically, the leftmost digit, basically every digit besides the leftmost digit represents its place value, but then the leftmost digit represents a negative value to allow negative numbers to be stored. So this is how you store -6. Anyways, this means that, right, to get the least significant bit, you can do x and minus x. So for example, if you want to find the least significant bit of 6, it is 6 is 0, 1, 1, 0, so you get 0, 1, 1, 0 bitwise and 1, 0, 1, 0. And if you evaluate it, you'll get like 1, 0, which, or 2. Wait, do we explain how bitwise n works yet?
Bitwise is used for sandwich trees, which we'll learn like tomorrow. So, but I don't think it's really necessary to learn how it works.
Fenwick is like
So bitwise. Wait,
next Tuesday. Wait. Yeah, Fenwick is next Tuesday. It's not.
So bitwise and wait, anyway. So bits can be used for subset brute force, like, or for example in general for bitmask problems, where you can easily store subsets. So you can represent an integer as a state, where the ith bit being turned on means that the ith item is selected. So in particular, you'll find out whether the ith bit is selected by using bitwise n of the bit mask with one left shift I. So wait, do I need to illustrate it? Okay, wait a second. Okay, so for example, let's say that we have a number 0, 1, 1, 1, 0 in binary, okay? And then right, this is the 2 to the 0 position, the 2 to the 1 position, the 2 to the second position, 2 to the third position, and 2 to the fourth position. So this number is 2 cubed plus 2 squared plus 2 to the first, which is 14. And then let's say that we want to bitwise, and then let's say that, right, we want to find if the second bit is turned on. So the way we will do this is that we'll bitwise it with 2 to the power of 2 squared, which has this bit mask. This is 2 squared. And then, right, we'll bitwise n. So the way we do so is that we bitwise n digit by digit. So for example, 0 and 0 is 0. So this bit is a 0. And then, right, 1 and 0. Since there's a 0 here, this bit is 0. 1 and 1, since both bits are 1, we put a 1. 1 and 0 is 0. And 0 and 0 is 0. So since this So since the bitwise end result we get is non-zero, that means that the second bit is turned on. Anyways, like to actually brute force, you brute force all the bit masks. So yeah, like the bitwise end will only filter out the ith bit for you. Wait. Okay, and then there's this thing called floats, where bit operations are very complicated. If you need more than 64 bits, like for example, you want to store big mass of like n where size n where n is up to a up to a bigger number, you can use this thing called bit set. The disadvantage is that its size needs to be known at compile time. So like this is okay, but this is okay, but you cannot do bit set, bit set and wait, sorry. So you can do bit set 1000, but you cannot do bit set n. The thing about bit sets is that they are very fast. Like they require 1/64 the time of just using booleans, and also the memory is much less. So that means that you can do some very good scams, like this Codeforces problem. Wait, should I leave them time? Should I give them some time to actually try that problem?
They don't even have a Codeforces account. So it's 1700 return.
Wait, no, it's I think we
Okay.
just
What?
there's some like bitmask like the 2n brute force problems on Codebreaker. I think we can let them try that.
No wait.
Okay.
Don't try
Just
the
use-
problem. The Codeforces one is like bitmask DP or something like that. Don't do that.
Yeah, like we could just like make them do like binary coins or bowback.
Yeah, do the MITM problems. You can do 2Ns and try to 2N.
But like they haven't learned MITM yet.
No, as in 2N, there's probably a subtask for 2N brute force.
Yeah.
So if you want, you can try to so if you want, right, you can go to Codebreaker, then go to problems, and you filter problems, then just use the meet in the middle tag. Even though like you probably wouldn't AC with 2 to the power of n brute force, you'll probably get some marks. Yeah. So like bowback, hard disk,
Stoning.
stoning,
Black magic.
Yeah, stoning. Black magic. No.
Yeah, black magic is like the deck cost question. It's the it's the deck cost thing.
Oh. Oh, okay. Got it. Yeah, you can also use the bitmask tag lah, I think. Yeah. Hard disk also. Wait, yeah, hard disk is MITM right now.
Wait, Brian, do you want to do one question just to demonstrate?
Okay, which one though?
I think just like do black magic. It's like
Okay.
just like do the bit mask, like the brute force part. Because like it's quite complicated. I think that
Okay, sure then.
we need to do that. Alright, guys. Alright, so Brian is going to live code black magic.
Okay, so first we need to read in the input. What's the maximum possible answer?
What does your temper monkey do on Codebreaker?
It just changed problem to Bugaboo. Ignore that.
Okay.
There's a time when they decided to replace problem with Bugaboo on Codeforces. So we read in the input. Yes. Okay, so now we need to test every possible subset of the spells that you use. So the way we do so is using a bit mask, and the bit mask has m bits, so it goes from 0 to 2 to the power of m. And we shall compute the cost you need to activate this subset.
Brian, you pause first. Let me explain something. So like, you might have seen how he wrote the one arrow m in his for loop. Basically, you're shifting 1 to the left by m. You're shifting 1 to the left m times. So essentially, what you're getting is 2 to the power of m. Is that clear? Because like this is how we're going to like try every combination for like the m, which is up to 10. But because it's up to 10, because it's very small, we have enough time to do it, even though it's like a 2n time complexity, but we can still do it because m is only up to 10. Alright, Brian, I think you can continue.
Okay, so anyways, we need to test if this bit mask is valid, as in like it successfully disables all the defenses. So the way we'll do so is that we'll just check the block value of like each guy. So like, wait. So in block 101, so we initialize this block array to 0 because initially it has block value 0. And then after that, we apply all the spells. If we are applying the spell, is we do I and 1 left shift J. And then if so, then we'll apply the spell. Wait, this should be J. Okay, I should make my code more readable. So now we just need to check that the condition is held. So we shall check each so we shall check each of the defenses and check that they have a block value larger than CI. So the way we do so is that if there is a value which is less than C, less than C of J, then we know that it's invalid. So now if it's valid, we'll update the answer. And then
Wait, you have
just need
to
test
you
it.
like calculate the cost as well.
Oh, I did it here.
Oh, okay.
Wait, why is it saying that the answer is... Wait,
No, cause
hold on a second.
yeah, you only like add a cost if you are using the spell. It's like it's in the
Yeah, I did check for that.
no. It's like you only like here like your CUR plus equals DJ is not supposed to be there. It's supposed to be like in the
Oh, okay. Sorry.
yeah. Right.
Okay.
Now that works.
Okay.
Alright. Wait, can you go back to the code? Like go back to the bit mask part. Right, just so like does anyone have
Yeah.
any questions about the code?
I have a question like when you should use bitmask for like problems.
Bit mask you use it when like your n is really really small. Like in this case like n less than 20, m is less than 10. So you can like afford to basically like try every combination because yeah,
So it's essentially just a brute force.
yes.
Oh.
But like sometimes you have to use it because it's like because like in this cases like this it's really hard to just calculate the answer directly, but it's easier to brute force and then check if if just like brute force all the solutions and check if it works.
Wait, but like
Wait, I'll leave now for a while.
stoning is
Yeah. Can you ask again? I didn't hear that.
yeah. For stoning like as in like the code breaker question,
Yeah.
the scoring is like 10 to the power 15 though.
Stoning. Hold on,
It's like
let
the
me,
lowest is 10 to the power 15. Okay.
let me
And for A and B it's also 10 to the power 14. So like is it possible to brute force it?
No, but because like n basically like in stoning like each citizen can have a or b, so like that's like the binary, like it's like either this or that, and then there's only up to 40 citizens because the constraints on n. So there's like for stoning you can't do like brute force by itself doesn't work because 40 is too big. It's like it only works for up to like 20, around 20. So like you have to basically like split it in half and then calculate separately and then combine it together, which we will teach somewhere in the future. Hold on. We'll teach
But can't you
during
just use like
day 4
oh okay.
under
I
like
was trying it with sorting just now.
yeah, because like that's the thing about
Sorting.
it's like I don't think you can solve it with sorting because like it's more complicated.
Oh.
Wait, should we give them some time to implement?
Alright, you can you have some wait give them I think we give them until like 2:50 to try out and then we'll
Okay, then.
check back. If you have any questions you can just ask us. Alright guys, we probably have to continue now. Alright, we have to, yeah, we are running out of time. We have to continue now. So if we want to like if we want to continue working on the problem, we can like do so after the lesson. But right now we have to go back. Alright, so after this, alright, so now we'll be talking about prime numbers. Right, so yeah, like this is a definition of a prime, but yeah, it's quite simple. So basically, first we'll be doing like prime checking. So we like the easy way is to just check if it's divisible by every number up to itself, but that's O(n), which is too slow. So we can, like, a smarter way of checking is we just check up until square root of n, because like let's say we have 18. If we divide by 3 is 6. If we divide by 6 is 3. So like you see how it's like reversed. So technically we only need to check up until square root of n, because if there's nothing from 2 all the way up until square root of n, then there's no point checking the rest. So we can check in O square of n time. So yeah, that's quite easy to implement. But let's say, what if we need to check a lot of numbers? Then this also isn't enough. So we basically need to, in a way, like pre-compute all our values. So basically we use this to basically eliminate all the prime number. We can basically use this to eliminate all the non-prime numbers and just runs in O log n time. Alright, so for primes, alright, so for prime checking, we can you can attempt this problem. And then for this, you can try this. For the sieve of whatever, you can try n prime. And try n prime and try n prime and x prime, and then yeah, so like you just try some problems for primes.
Can you put the code breaker search account down? It keeps on like hanging my computer for a good 1 minute every time I search for a problem.
I'll just send the links. Alright guys, do you need Brian to live solve all three problems? Because we're going to have to move on very soon. Because like for tomorrow there's like DP2 is a very big subject, so we are planning on like trying to start on it a bit today. Hello? It's like, is anyone there at all?
Yes.
Alright. That's crazy. Alright, so we have alright, okay. Okay man. Alright. So like this, I think we're just gonna wait until like 3:10 and then we'll move on. It's like prime checking is like quite simple. I think you can just like thank you. Alright, it's 3:10 now. We're going to move on. Alright, so next up we have base conversions. Like, I don't know if you're ever going to have to be honest, I don't know if you're ever going to have to use this, cause like I can't remember like when I had to last use this, so we're just gonna teach this. So basically, like I think everyone knows like how bases work. So like this is, so we have 7 to the power of 0, so it's 1, 7, 49. And then basically like the number here you just multiply and then you add them together. But if we want to convert between bases, we have to check if, let's say we want to convert like 215 to base 7. So first we check, because so we check like 7 to the power of 3, so that's 343, which is more than 215, so it appears 0 times. And then we move down, so we divide, so that's 4 times, and then so on, and then we get the remainder, and then you just continue until we don't have any more. So that's how we convert them. So yeah, this is the code. Yeah, like I don't really care, like I don't think there's like a problem on Codebreaker for this, so like you can just like copy the code, I guess. Alright, any questions before we move on to DP?
I think that's XOR B where you have to convert to base B and then back.
Alright, so like I guess you can try to do XOR. Can I give you like until 3:25 to before we move on to DP? So like if you have any questions, just make sure it's done before then. Has like no one solved XOR yet. Alright, we're going to be like moving on very soon, so if you haven't solved it yet, I think we can we'll still have to just move on. Alright, we'll wait until 3:25 and then we'll move on, I guess. Yeah. Alright, well, we are moving on right now. Guys, are you still there?
Yes.
Alright. Okay, that's good enough. Alright, so hi, we are now at DP2. Alright, so basically DP2, is basically two-dimensional DP. So like, does everyone know what 2D arrays are? Alright. So like this is like a classic Math Olympiad problem, like from primary school. So like basically like you start at the top left, and then you want to get down to the bottom right, and then like if it's an X, you can't go there. How many ways are there to go from the top to bottom? Yeah, it's just like math. So basically for these, there's only like one way of getting here, which is from the left. Same from this. So it's basically the same value as this. And then this is also the same. So there's only one way of getting from here to here, which is to go from the cyan to the green. There's only one way. So it's the same value as the cyan, but from here you can either get from up here or to the left. So it's 1 plus 1, which is equals 2. And then for this one, because you can't go there, so there are 0 ways of doing this. So you can just think of this as 0. So it's the same. You can either go from here or here, and then because this x is 0, so 3 plus 0 is still 3. So there are 3 different ways to go from the top left to the bottom right. Right, so now like go AC flybot. Who was that?
Wait, what if I've already AC'd Flybot before?
Alright, I'll just continue then.
Okay.
Alright,
Wait,
extra.
I think some people like won it last year's North Course though, so like I don't think they did Flybot.
Jonah,
Right.
have you done like Mushroom 6? Have you done Collect Mushroom 6?
Yeah.
Not Josiah, Jonah.
Yeah, I've done Collect Mushroom 6.
Okay, wait.
I think like is like anyone else still there?
Wait, are you like fixing robots again?
Okay, who hasn't done Flybot?
Forget about who AC'd flybot. Who is there?
Anyone who is here just like react.
I think
Alright, we have we have like Jonah, Joseph, LaShawn, and myself. Alright, that's great. That's great. And Yuvraj, wait.
No, Yuvraj. Yeah,
Yuvraj,
yeah.
have you AC'd flybot yet?
Okay. Oh, Zisi's here as well.
yeah, this is there too.
Okay.
Okay, we have like 30 minutes, so like okay, I have to do something that's mandatory in every like North Course towards the end. So like
Oh, no. Josiah, I'll remove your expo role.
That was not like half of it, wasn't it? Okay.
Half of it wasn't you.
Yes, half.
Jonah, do you
That was
do you
you,
wanna,
the other
like,
half was
since you done Flybot already, you want me
Yeah,
to
you
go
can
to
remove
SimCity with you?
Obviously X or Co.
Jonah,
yes.
you wanna hop in another call? I'll go through SimCity with you.
Oh yeah, gotcha. Thank you.
I'll just like call you.
Wait, how do I like?
There's like
Yeah,
3
I'm
other
good.
PCs up there.
Okay, I'll leave temporarily. Yes, I'll be back in like a couple minutes. Yes, thank you.
Alright, Yuvraj, I haven't seen your submission for flybot yet, so could you go try that?
God.
Alright, has anyone here not solved Flybot yet? Alright, okay, I'll just move on. I assume everyone here has solved Flybot already. Alright. Alright, so now we have 2D static sum. So here's a recap first. Basically, a 1D static sum, this is what it looks like. So basically the static sum stores the sum all the way up until where it's at. So like this -1 is 8 plus 1 minus 10. And so if you want to find out a certain range, you take this at the end of the range minus the thing at the start of the range. Alright, that's easy enough. So collect mushroom 6. Alright, does anyone need me to go through collect mushroom 6? Has anyone not solved it? Alright, I'll just go through collect mushroom 6. So basically, the distance must be at most t, and a mushroom needs at least k sprinklers. So, but the problem is that we can't do brute force because, yeah. So but the thing we have to know is that the grid is static, it doesn't change, so that allows us to use 2D static sum. So like, let's say we want to find the sum of this purple block of things. We'll basically make our 2D static sum array first. So this is basically, so like if we are storing a number in the blue box, we're basically saying that we are storing the sum of all the numbers all the way from the top left corner to where the blue box is. So like if the blue box is here, it stores the sum of all the numbers in the purple and blue boxes. So basically, like, this is, if our actual array looks like this, our static sum array will look something like this. Does everyone understand that? I assume everyone understands. Like, if you don't understand, like, try to sound out like immediately so that I can go through and you won't be left behind. Alright, we'll continue now. So like we'll usually one index it, so that means like we have a additional, we just start from 1, so when we make our arrays, we make it a bit bigger so that it doesn't like eat into the edges. So basically, but because when we are querying, we might not be querying the whole thing starting from the top left hand corner. Let's say we only want to find, let's say, this box highlighted in blue. So like, how do we find that? It's like we can basically take this first, and then we minus this, and then we minus this. But because if you see here, we minused it twice, so it's overlapping. So we need to add this back. We need to add this part back. So that's basically how we can get it from our static sum. So basically, yeah, so we basically use the principle of inclusion and exclusion to basically find out find the sum that we want. Right, but we can also use this. We also need to use this where we actually pre-compute our static sum. So basically, let's say we want to create our static sum array, and we're on this number right now. So because we can't just like go on and add all the numbers in this box, because that would take too much time. But we know that because we already have pre-computed all the numbers from here all the way to here, so we can basically use these numbers to help us calculate our static sum. So we can just add this. We can add this box, and then add this box, but because this box in the middle is overlapped, we just minus it off again. So now we can basically get the sum of all the numbers in the purple squares, and then plus the number in this square, and we can get our static sum arrays. So the same thing goes for the querying, which is what I said just now. Alright, so now because of this, we can have OHW, which is basically like the height times the width pre-computation, and then queries can be answered in O1 time. So basically how we check it is basically how we implement this in Collect Mushroom 6 is we just assume sprinklers are 1s and everything else is 0. And then for every mushroom, we just check the distance. We check a distance of D around it. So let's say if D is 1, we just check this whole chunk to see how many sprinklers can reach it, and then check if it's more than K. So now everyone go try and AC Collect Mushroom 6.
How many trainees are there actually?
Like how many? Like you mean how many alive trainees or like total trainees?
Alive trainees.
I don't know. I think like you've Raj like reacted with something, but I don't know about the rest.
Also, I need to go like now. I should say.
Alright, you can go now. That you can just we have the recording later.
Bye.
Alright, bye bye. I go try collect mushroom 6.